welcome. I was really surprised by a very precise schedule, and I would like to stick to it. So, therefore, dear Ms. Gruber, distinguished awardees and honorable guests, it's a great honor and a privilege for me to be here today on the occasion of the presentation of the Gruber Cosmology Prize. Each year, this prestigious award recognizes those outstanding cosmologists, astronomers, and astrophysicists whose work have in some way changed our perception and understanding of the universe. I would like to take this opportunity to extend my sincerest thanks to you, Ms. Patricia Gruber, President of the Gruber Foundation, for creating this award jointly with your husband, Peter. This prize is not only a great distinction, it is also a great opportunity, of course, for scientists, enabling them to continue making fundamental advances in their field. Thank you very much, Ms. Gruber. As an organization dedicated to the pursuit of scientific excellence, the Max Planck Society is especially delighted that Simon White, one of our directors, is among those being honored today. Peter Gruber, chairman of the Gruber Foundation, once said, "Cosmology is the most scientifically rigorous, aesthetically elegant, and the most poetic of the sciences." No doubt, ladies and gentlemen, all of you present here today agree with this sentiment. And I'm sure that, just like myself, you are all looking forward to this afternoon and an evening in honor of those who have dedicated themselves to continuously increasing and expanding knowledge in the most poetic of sciences. I wish you all very enjoyable and inspiring hours to come. And now, ladies and gentlemen, please welcome our honorable host of this great event, the President of Gruber Foundation, Ms. Patricia Gruber.
Thank you for those kind and generous words. We want today to welcome you to the 12th presentation of the Cosmology Prize, honoring a leading cosmologist, astronomer, astrophysicist, or scientific philosopher for theoretical, analytical, or conceptual discoveries leading to fundamental advances in the field. We are delighted to be here at the Max Planck Institute for Extraterrestrial Physics to present the prize. Thank you to General Secretary Kronthaler for welcoming us so nicely. The Cosmology Prize, established in 2000 as the first of our international prizes, is presented in conjunction with the International Astronomical Union. Let me introduce Ian Corbett, General Secretary of the IAU, who will say a few words about our collaboration.
Thank you very much, Patricia. The IAU is delighted with its long-standing and highly effective collaboration with the Gruber Foundation on this Cosmology Prize, the fruits of which we are celebrating today. We have 4 outstanding laureates, adding their names to what is a very distinguished list that runs before me. But for me, this is a double pleasure. The event itself, and also the fact that I have known and admired the work of the recipients for some considerable time. I can even remember arguing with Carlos over the funding of a supercomputer that he wanted to buy, which I wouldn't let him. More importantly, in some ways, it will not have escaped your notice that recipients of the previous Gruber Prize have become Nobel laureates, which shows that our advisory board, 3 of whose members are put forward by the IAU are somewhat ahead of the curve. I should issue a warning to our 4 laureates today, but who knows? But the collaboration has another important and additional component. The foundation supports a fellowship, a program which allows outstanding young astronomers working in any field of astrophysics to work in a center of excellence of their choice. You will note that the development of astronomy is the main goal of the IAU. So the Gruber Foundation's fellowship program is a very important part of the IAU's work and is a highly valued contribution for which Patricia is grateful. The 2011 Gruber IAU Fellow is Jaime Guerrero Romero, and I will ask Jaime to say a few words about the work he's about to undertake in Berkeley and California.
Well, thanks to the support of the Gruber Foundation, I will be researching in Berkeley basically on the work I have been doing, galaxy formation in a cosmological context. But I will be focusing on galaxies, on the faintest galaxies we can observe today, trying to infer their physical properties, but not only that, but also trying to make predictions for the next generation of telescope, like the JWST telescope or the next 40-meter glass telescope.
Thank you very much indeed, Jaime, and I'm sure everybody here wishes you every success in your tenure of the fellowship. It falls to me, on behalf of the IAU, to say that it is a great pleasure to thank Peter and Patricia, Gruber Foundation, and Peter and Patricia, particularly and personally, for all that they have contributed to our work. I don't think I can find the words to thank them enough. Thank you.
While my husband, Peter Gruber, can't be with us today because of his health, I would like to acknowledge his vision and leadership in establishing the Foundation's prizes. Peter was a boy who, being Jewish, fled to India from his native Hungary, as many of you know, during World War II, along with his family. When the Japanese bombs fell over Calcutta, the family sent the children away to the Himalayas and the hill town of Darjeeling to study in a Jesuit school where they would be safe. It was there that Peter helped the fathers in the garden, and as a reward, he was allowed to look through the telescope at night, which you can imagine at that altitude. It was this experience that led in part to establishing the Cosmology Prize. While he can't be with us today in person, he sends his warmest congratulations today to the gang of 4. In keeping with Peter's and my wishes, we have recently enacted a succession plan for the Gruber Prize program, and we're very pleased that it will continue indefinitely, in perpetuity, at Yale University. 3 science prizes will retain the same format, including the IAU Fellowship, offered as an example today to Jaime, and to promising young investigators working in any field of astrophysics. The missions of the Justice and Women's Rights Prizes will be carried on by the Yale Law School, and they will evolve into a different format at Yale. We are here today to honor the achievements of Marc Davis, George Efstathiou, Carlos Frenk, and Simon White for having provided a powerful tool for comparing theory and observation on cosmological scales, and using that tool to validate the cold dark matter theory of cosmic growth. But first, let me tell you a little about the company they're keeping with our other prizes. The Foundation's prize program was established in the year 2000, and it currently presents, sorry, that would really be an unfortunate circumstance. It currently presents a total of $500,000 prizes in the fields of cosmology, genetics, neuroscience, justice, and women's rights. Each prize recognizes the achievements and discoveries that produce fundamental shifts in human knowledge and culture. On September 26th, the Women's Rights Prize was presented to Avega Agohozo at the Yale Club in New York City. Earlier this month, the Justice Prize was presented at the National Constitution Center in Philadelphia to Barbara Arnwine, Morris Dees, the Association for Civil Rights in Israel, the Center for Legal and Social Studies, and the Kurdish Human Rights Project. On October the 13th, at the 61st annual meeting of the American Society of Human Genetics in Montreal, the Genetics Prize was presented to Marc Davis. Next month, the Neuroscience Prize will be presented at the 41st annual meeting of the Society for Neuroscience in Washington, D.C. to Huda Zogby. And now returning to cosmology, the past laureates of the Cosmology Prize are Charles Steidel, Wendy Friedman, Robert Kennicott, and Jeremy Mould, J. Richard Bond, Saul Perlmutter and the Supernova Cosmology Project, and Brian Schmidt and the High Z Supernova Search Team, John Mather and the COBE team, James Gunn, Alan Guth, Andre Linde, Rashid Alyevich Sunyaev, Vera Rubin, Martin Rees, Philip James E. Peebles, and Alan R. Sandage. These prize recipients this year were chosen by our distinguished advisory board: Jacqueline Bergeron, Ronald Akers, Wendy Friedman, who has served as the chair, Helga Krog, Andre Linde, Julio Navarro, and Roger Penrose. Owen Gingrich and Virginia Trimble also serve as special cosmology advisors to the foundation. Peter and I deeply appreciate the knowledge, the commitment, and the enthusiasm that these advisors bring to the judging process. I would like to now introduce our executive director, Sarah Rea, who will read the prize citation and introduce today's recipients.
Thank you, Pat, and good afternoon. The official citation to the prize reads, "The Peter and Patricia Gruber Foundation proudly presents the 2011 Cosmology Prize to Marc Davis, George Efstathiou, Carlos Frenk, and Simon White for their pioneering use of numerical simulations to model and interpret the large-scale distribution of matter in the universe. Cosmological simulations allow direct confrontation between observation and theory, and have transformed the way we conceive and visualize the growth of structure in the universe. The work of Professors Davis, Efstathiou, Frenk, and White galvanized support for cold dark matter as the dominant form of matter in the universe, and has thus been instrumental in the crafting of our current cosmological paradigm. I will now read the remarks of Wendy Friedman, the chair of the Selection Advisory Board to the Cosmology Prize and a 2009 laureate of it, who is unfortunately unable to be here with us today, but whose words I am pleased to share on her behalf. I am now Wendy, to be clear. I am delighted to send these remarks in celebration of these four exceptional astronomers, the Gang of Four, as they are affectionately known in the astronomical community. The recipients of the 2011 Gruber Prize in Cosmology. I won't say cosmetology. I send my sincere regrets. A confluence of events this month has been such that I am unable to join you all in person, but I certainly join you in spirit. In the last few decades, an entirely new standard picture of cosmology has emerged, a universe made up of approximately 30% matter, most of it dark matter, with the remaining 70% made up of dark energy. In the 1980s, as new detectors became available on astronomical telescopes, large surveys of the sky revealed, unexpectedly, that the universe is filled with structure, giant walls of galaxies, long filaments, and giant voids. How this structure arose was not immediately clear. Did the structure form from the top down with giant structures that subsequently fragmented? Or did the structures form from the bottom up and grow into larger structures? Davis, Efstathiou, Frenk, and White undertook computer simulations to show that these structures can be understood as a result of tiny differences in the density of the matter arising from quantum fluctuations in the early universe. Owing to the attractive force of gravity, the higher density regions in the universe become denser and denser over time. The quantitative predictions of these models are remarkably consistent with the observed large-scale structure in the universe and have provided a physical understanding for the growth of structure in the universe. These models require that most of the matter in the universe is cold, that is, moving at speeds that are slow relative to the velocity of light, and dark, that is, comprised of a form that does not emit light. Together with observations of the accelerating universe, which suggest that 70% of the universe is made up of dark energy, these results have led to the current standard paradigm for cosmology. The Davis, Efstathiou, Frenk, and White papers were instrumental in ushering in a new era where numerical simulations became a standard tool of cosmological studies. To Marc, George, Carlos, and Simon, I offer congratulations on behalf of the entire Selection Advisory Board to the Cosmology Prize. It was the unanimous recommendation of the committee that the prize be shared among the four of you. It is my sincere pleasure to participate from afar in this ceremony. I have known all of you for several decades now, followed your work over that time, and seen the impact that it has had. I wish you all a most enjoyable ceremony. Wendy Friedman. Marc Davis, George Efstathiou, Carlos Frenk, and Simon White, please come forward to receive your prize.
No, Mark, it's 2 minutes.
Yes, right. I forgot, I had a 2-minute speech. I want to thank the Gruber Foundation for the wonderful announcement and to allowing us to complete our kitchen. What?
One of the space stations.
Oh yeah, space station, right. But this is a most unexpected prize, and I am so happy to have won it. And just think about the winners who had before me, and all the people, and they were excellent. And I just can't get over that we are up there with Jim Peebles. I think it's a highly ranked award. Thank you.
I'd like to thank Peter and Patricia Gruber and the Gruber Foundation and the Advisory Board for recognizing our work. I'd like to use this occasion to express my deep appreciation to my collaborators, Marc, Carlos, and Simon. It's been a privilege working with you guys. I had no doubts at all at the time that we were doing the work that it was important and would have lasting value. But as Fred Hoyle said, if you ever achieve anything in science, the world will conspire to make sure that you never achieve anything again. And, you know, as we've become more senior, and we've had committees to deal with, departments to run, and so on, it's been difficult to maintain that kind of intense collaboration with your contemporaries. So I'm delighted that we've got an opportunity with the talk that you're about to hear. The four of us have arranged a tag team presentation, and it gives us an opportunity for the gang of four to ride again.
Well, it's of course a tremendous honor to be a recipient of the 2011 Gruber Cosmology Prize. The last 30 years have seen really spectacular advances in our understanding of the universe and the structure of the universe, as evidenced, for example, by the fact that 2 of the last 4 Nobel Prizes in physics have been given for work done in cosmology. As all of you will know, my 3 fellow gangsters here are all very distinguished. They're all extremely hardworking, inspiring scientists, but I think that alone would have not been sufficient for them to do the work that led to the award of this prestigious prize. I think another key factor was to be in the right place at the right time, and above all, to have the courage to challenge the received wisdom and the scientific establishment, as we did at the time. Of course, what happens after you do that is that you yourselves become the scientific establishment. So I look forward now for the next generation of young scientists who come along and challenge what we represent. Of course, getting the Gruber Prize is a wonderful thing to happen in any circumstances, but to share it with these 3 colleagues makes it even more special, because these are really 3 truly special individuals with whom I've not only had the great pleasure to collaborate scientifically in a very productive way, but also to enjoy the most wonderful friendship. So let me finish by thanking the Gruber Foundation for, of course, the prize, and also for everything you do to support this wonderful, poetic, and inspiring science. Thank you.
So of course I would like to add my thanks to Peter, Patricia, and the whole Gruber Foundation, both for awarding us this prize, and but more importantly for supporting our science and giving us ways to celebrate it. It's very important. And I think what I particularly like about this prize, apart from the fact that I can think of things to do with some prize money also, is that it recognizes the fact that computer simulations have actually become an important part of our science, and now have become another tool in addition to traditional theory and to observations in pushing forwards our understanding of the universe. And I think this is something which has changed as a result of the way that computers have got stronger, and I think I'm glad to see it recognized, because it's been, of course, an important part of my life, as has been this collaboration. So it's a great pleasure for me not only to receive this prize, but in particular to receive it at Frenk. So thank you very much.
Congratulations to all of you again, and we will now hear from each of them in the lecture, which we understand has not been rehearsed. Much the way they collaborate is spontaneous, and it's going to work somehow.
Okay.
Okay. That's just right. All right, fine. Okay. Okay. The first of the lectures will start with, if I can remember how to start this thing. I'm going to first speak about how the surveys that we undertook. Is it on? Okay.
It was fine before.
Okay, fine. How the surveys began. I came to Berkeley in 1981, I think it was, and I wanted to follow. I was coming to work with Simon. Simon at the time was a non-tenured professor at, not even professor, he's a non-tenured faculty or staff member at Berkeley. I was coming to Berkeley answering a faculty job. I wanted to go with Simon, but on the other hand, there were a few things that attracted me to Berkeley, like the snow and stuff like that, but that doesn't matter. So what I had come from was a large survey of galaxies that took an enormous amount of time. You may think this is crazy. It took us 2 years to measure 2,000 redshifts. That's about the work you would do in 2 nights now on any medium-sized telescope. But 2 years, you remember it well back there. And we did it all on a 60-inch telescope at Mount Hopkins, 200 nights over a 2-year period. We got 25 clear nights, 25 clear galaxies per night, and we collected the galaxies one by one by one by one. But we had this data when I was done that I couldn't understand. Nobody could really understand it, and I came to Berkeley to work with Simon on it. Now, this was the original Center for Astrophysics first survey, and it told us about the filamentary structure of the large-scale universe. It was a big surprise to everybody because it really was unexpected, and people started to wonder what it would mean. So Simon and I hired Carlos as a postdoc, and we used the best code we could find, and that was clearly from George Efstathiou, who had worked on it as a student and who had given me an early version. And we decided, well, we're going to use the best. And so we got together and started working on this. And this is how the Gang of Four was born, deliberately. Okay, come on. Okay. Hang on. All right, so here's us in 1981. Simon's hair is similar. George looks about the same. Carlos, George is the same. Carlos has a mustache. I had a mustache as well. I have more hair, but you know, we're about the same. We've lost a little weight, or haven't gained weight since then. But this is the gang of us. And Carlos was, all right, so we started working. And what did we do? This thing doesn't work at all. All right. So the idea was to understand what the universe can tell us about this. This is what we learned in the first CFA survey. The universe showed lots of galaxies and filamentary structures around the sky. This tells you where they are. This is the northern cap, and here is the region of the sky, the redshift slice. These are the first time these plots were made by anybody, and you've now seen them in many plots and many literatures. But this is all the same stuff. 1981 or so. This is a paper preceding our work. This was dated from 1982, when this was published, the first CFA redshift survey. All right, so how can we explain that? Well, I thought we fixed this. Okay, fine. All right. I was using a 20,000 body n-body simulation that was run by George Efstathiou and Steve Eastwood. Okay, now here is what it was. This is the best we could do. The models didn't have filamentary structure. Compared to the previous picture, it had these incredibly dense clusters. Really dense here. Here they're dense, they're elongated, but there's nothing that looks like our universe. And yet this model was about the best that existed prior to the work of Linde and Guth, sorry. About as good as could be devised. Nobody really had any idea of how to make this structure work better. So we knew this wasn't good enough, and we wanted to make a better model. There was no way you're going to make a better model except to study it with computers. The computer we had was this thing. This lovely computer, which is, people have their laptops with junk, this thing. This is a VAC 780, of which about the power of an 8086 processor. Or I don't think it's that powerful. But it has, after all, 2 megabytes of usable memory and 4 megabytes RAM total. One processor, 1 megahertz, and it's right up there. It required a huge room. I mean, not quite this large, but a big room, and the room was air conditioned, thousands of pounds, et cetera, and it was quite an enormous undertaking to have this. Now, this is, of course, the only computer you could have in your department because these things cost a lot of money, and therefore it was hard to get time on them. And we wanted a lot of time. We knew this was going to take a while. We wanted greater than 50%, and we wanted it for more than 6 months' time. We just wanted to own the damn thing and keep everybody else off of it. And we had to make backups in case it crashed. You know, we didn't have automatic backups in those days. You had to make sure that the thing wrote something out every day, otherwise you're possibly going to lose the job. But this was it. This is the computer for the entire department 30 years ago. Right? That's what and Virginia remembers this very well. This is a big step up from what we were before.
I'm not the oldest person.
I know. Yeah. Well, we all suffered. Now, in the old days, we had such problems as how do you specify the initial conditions? The power spectrum of the power law we wanted to simulate is the blue curve. The red curve is the hot dark matter model, which has a cutoff. They were simulated separately. But with 32 cube particles, which is as many as we could ever run, that's a lot of particles, especially if you've got to get them shoved into the memory. This thing, it allows us to specify 16 waves in each direction. 16, a math factor of 16 is this much, and so you can specify this much at a time, and you had to be careful about how you put it in and how it overlaid with the other ones, and et cetera, et cetera. We had to understand this thing that nobody understood how to use. We read about it, but we didn't use it much, and this is known as the Zildovich approximation to specify delta how to specify the fluctuations in density and velocity. This is critical to be done correctly rather than the old silly ways we put these things in. We had a lot of debate about how this should be done, and we figured it out and published the results in 1983, just before we were ready to go ahead. Okay, and so we had to run for 3 months at a time, and we had to be very careful, but we didn't, well, I'll let somebody else tell about this. There was a Fortran mistake that was made in our programming. You may wonder why our file is labeled at, what was it, 32 and a half megaparsecs on the side. It was really supposed to be 25, but we scaled it to make best use of this mistaken input. We won't say any more. Okay, but eventually we got the the simulations work very, very well. And I've shown this picture to people around the world and asked, for a show of hands, which one is real data? Anybody? 2 of those are fake, 1 of them is real. Anybody?
Top left.
Sorry?
Top left.
Top left? That's real. Oh, who says top left? All right. Bottom left. Bottom. Right. Upper right. All right. It's about it's about right. About equal votes. And so that this worked. It was the bottom. It's the center. The bottom. So this shows that what you're looking at is a CFA1 survey against 2 fake simulations. And after this, we knew we were onto something that worked. It was tremendous, tremendous fun reaching this point. But now, the situation is insanely better. Here is real data. This is real data. This is a CFA. This is our original CFA survey enhanced with more data. And these are all fake simulations. This is 2006. This is only after 21 years later. The field has advanced that fast. It was astounding how the field took off. But you know, in one way, we knew what the answer was after we did the first simulations. So I changed gears around something else. And other people continued to make these better and better models, but boy, the field really exploded after we got out of it. Not all of us got out of it. After we moved on. Okay, I think that's about it for me.
Okay, so thanks, Mark. So I'm going to take you through a little bit of a historical tour of the development of numerical simulations. The basic problem is a Newtonian problem. It was known to Newton. There's this terrific quote from Newton to the Master of Trinity, in which he talks about how he thinks structure in the universe formed. So the universe has to be infinite to prevent everything collapsing into one blob. And if there are little irregularities, the universe will fragment into separate structure. Another interesting thing, he even thought about the possibility of dark matter. So you could explain the formation of stars if the material is luminous. The problem, of course, is that to do this, we can solve the two-body problem analytically, but we can't solve the general n-body problem. And so we would have to use computers. And the difficulty is that we have n-squared interactions that we need to compute if we're going to solve this problem numerically. And so that's difficult to do. So another approach would be to divide the material onto a mesh. Fourier transform it, convolve with the Green's function, and get a rapid computation of the force. The difficulty with that is that when we want to understand structure formation, we want to be able to model high density contrast. The density contrast of our galaxy with respect to the background is over 1 million. And it's very difficult to use a mesh that's large enough to get the resolution. So we needed some other type of approach. And the approach is to solve the problem, to use a hybrid solution to this problem. I was actually a graduate student visiting Manchester learning about mesh codes. when I was told about a technique that had been developed by two computer scientists, Hockney and Jim Eastwood. What they'd done was they found, so this is a picture of Jim Eastwood. What they'd done was used a mesh computation to calculate a force. It's a low resolution force. And then developed a scheme where you add the difference between the mesh force and the actual force that you want to model by direct summation. So you only do that for near neighbor particles. And that gives you a rapid solution to the n-body problem. So I called up Jim Eastwood and I said, you know, I hear you've got this method and I think it might have applications to cosmology. And he said, yeah, okay, if you're interested, come down and visit Reading. So I did, and worked with him to adapt this technique to cosmology. Now these guys were computer scientists. They were actually interested in the method. And the applications that they were using the method for were small n applications in molecular dynamics, not in gravity. So I took a rudimentary code and then had to adapt it to do cosmology. This is the start of the code, revised code. So Carlos and co know that I'm not very good at documenting code. You can see that here. You see the small amount of documentation says you only need one common block there, and the actual file is it has a different name. That's quite typical. They adjusted to this. Okay. You'll also see that it's in uppercase. Okay. So I was visiting Reading and worked and modified this code, and I applied for time on a supercomputer. This is actually a picture of the exact computer that I used for my thesis work. So this is an IBM 360-195, and this was at the Atlas Center at the Rutherford Laboratory. The IBM 360 series was designed for business use, for banks. And I think the world would probably be a better place if the banks had stuck to 8-bit processors. But this machine was the Ferrari version of the IBM 360 series. The 360-195 was a fast machine. It had 2 megabytes of RAM. But to get turnover, to actually run the code, I had to get it to fit in under a megabyte. If your code went over a megabyte, you had long wait times in queues. So the code had to be done in under a megabyte. Input was via punch cards. That's why the code is uppercase. The lowercase bits that you saw were later additions when we had terminals. We could edit terminals. So you type things out on punch cards, and then a lady in amazing flared trousers would feed the punch cards into the computer. So that was the machine, and the thesis runs that Mark showed some of the output from the thesis runs had 20,000 particles. They took 70 hours to run in 2-hour blocks. Now, 2 years ago I moved office, and I was ruthless, and I threw out everything to do with my thesis work, including the slides that I'd made and so on. So I decided to recreate them for this talk. Okay. So I dusted off the code, which I hadn't used for 20 years, compiled this thing, and ran it with white noise initial conditions, 20,000 particles. Now, one run like this took 70 hours back in 1978. Okay? So Carlos, how long do you think it took to run on my laptop?
15 nanoseconds.
Come on. Carlos was never very good with numbers. No, this run, it took 30 seconds. 30 seconds, okay? And so here it is, I made a little mini movie. What you see is periodic. I thought you sorted this out. Press the arrow.
It's going, it is moving.
Is it? God, your computer is much slower than mine. Right, okay, so what you see, I'll just keep pressing. It shows the development of structure in the triply periodic, so it's an infinite universe, just a projection of the cube, and the number is the scale factor. And as the universe expands, structure forms. So the first time, so 20,000 particles, one of those initial conditions. The first time I ever showed these things as a graduate student was at an IAU meeting here in Munich. And I was fortunate enough to be placed to speak after Colin Norman, who showed pictures of galaxy mergers using 30 particles. And then I showed these slides with cosmological simulations of 20,000 particles, and it had quite an impact. So then from then on, Carlos Marc already mentioned that we made the first set of cold dark matter simulations on VAX 11780s. So these computers actually had microprocessors, and we had beehive terminals to input things. And in the UK, we had a network of newly installed VAX 780s. Ian will remember this was the Starlink network. So there were machines at major astronomical institutes around the UK. And Carlos and I used this newly installed network. We saw an opportunity over the Christmas period to load as many of these machines up as we could with CDM, cold dark matter runs. So these are my notes, which fortunately I didn't throw away. So there's some interesting things here. This is the power spectrum, specifying the cold dark matter initial conditions that Dick Bond, previous Gruber laureate, and I calculated. This shows the set of omega equals 1 runs and the computer that they were running on, Royal Greenwich Observatory, Cambridge, Royal Greenwich Observatory, and then the open universe models were running at Manchester and Edinburgh. So you see, back then we'd already discovered distributed computing. The other interesting thing for young people in the audience is to note that I'm writing these notes on New Year's Eve in 1983. So on New Year's Eve, this is what I'm doing. So to the young people, if you want to win a big prize, this is what you've got to do, okay? You've got to be committed. And this shows some of the actual original pictures of these runs. This is on Versatech output, so thermal paper that has survived 30 years nearly. So here are CDM initial conditions, and this was the important paper, the first paper that we wrote describing these results. That is my hand-drawn plot of the evolution of the two-point correlation function, and that's how it appeared in the journal. And then we progressed after the 780s to Crays, to vector machines, and now we had Pericon terminals in our offices that could do graphics. So that was a terrific step. And then you could do really big simulations. And that's really how the field has progressed. Ever bigger computers, bigger simulations, and this is a slide that Simon gave me showing how the particle number has increased with time. So Simon, I corrected misspelling of my name here. I also would quibble about the placement of this point, because the runs were done in 1978. It's just that I'm very lazy about writing things up. But you can see, the interesting thing here is the rate at which the particle numbers have increased. And that has, of course, a lot to do with the increased performance in computers. But it also has to do with improvements in the algorithms. And Volker Springel, somewhere here in the audience, has been a key person in developing better ways of solving this, finding hybrid solutions to the n-body problem. So I'll now hand over to Thomas.
I'm about to take off on this. Okay, so let me first of all see if Thomas can put the lights down a bit, because I got a movie that is not going to look very good in the light. Because what I'm going to talk about is the dark. The topic that I will discuss is the topic of where galaxies form. And as we know, galaxies form in dark places. They form in clumps of dark matter, which are known as dark matter halos. And then you can see here an artist impression, pretty poor artist impression, but nonetheless an artist impression of one such dark matter halo. So if we want to understand how the universe became structured, we need to understand how galaxies formed, and that required us to understand how these dark halos form. That's the key to understanding how the universe is structured. So the context in which we try to understand the formation of galaxies and halos is, of course, the Big Bang. But there were, in fact, two ideas, truly revolutionary ideas, proposed in 1980. One of them was the idea that the dark matter may have been a form of elementary particle, perhaps generated, produced when the universe was a mere 1/1000th of a second old. That was one of the two ideas. The other idea, which goes by the name of cosmic inflation, was put forward by two previous Gruber Prize winners, Guth and Linden. And the idea here was that at an even earlier time, just the tiniest instant after the Big Bang, the universe would have gone through a period of what we call cosmic inflation, a period of very rapid expansion that caused the universe to fracture, producing small irregularities that were the seeds for the galaxy formation that occurred afterwards. And these tiny irregularities, we give them the very nice name of quantum fluctuations. So cosmic inflation laid down the initial conditions, dark matter, a hypothesis for the dark matter, then led us to be able to calculate how these seeds would evolve. Now this idea that the dark matter may be an elementary particle is an idea that has dominated the subject of the last 30 years, a key assumption that dark matter is an elementary particle formed in the early universe, which is different from the particles that we are made of, particles in ordinary atoms. This idea is shared not just by scientists, it's gone beyond the scientific domain. Even politicians know that, like Angela Merkel, that the dark matter is a tiny little particle. And, you might not be surprised, he's a physicist after all. But this fellow here, David Cameron, for those of you who don't know who he is, he's the British Prime Minister. He too realizes what the dark matter is. If you don't know him, I'm sure you'll recognize it. He not only knows that it is a dark matter particle, but he knows that there are three types of dark matter. Of course, not all politicians are as enlightened as these two. Some get the wrong end of the stick. The issue of Obama, who's laughing because he himself knows that the look at Hillary Clinton here. I'll explain why she looks so puzzled in a minute. Anyway, so she says it to me, I must keep a straight face. Inflation provides the initial conditions for the formation of structure. If we know what the universe is made of, then it just becomes a physics problem to try and calculate how a structure grows. And that's where the simulations and the computers come in. because what these supercomputers do is they simply use the known laws of physics in order to calculate how small primordial seeds, these quantum fluctuations, grow into galaxies today. So these are the program. This was the program that we set out to do in 1981, and that is the program that many of us have continued working on for many years. So let me now explain why Hillary Clinton looks so puzzled. Well, Tony Blair knew is because, in fact, it was already known in the 1980s that the dark matter could be one of three different types, depending on the sort of velocities that these particles had. The dark matter could be hot, warm, or cold. Now, Simon White will tell you in a little while why we were able to show that hot dark matter was not really a realistic possibility. And we set that out. I remember very well the discussion we had in Berkeley. We set out to prove cold dark matter wrong. And that was 30 years ago, and we're still trying. So I often say that in a sense, we have failed to do what we set out to do. So in that respect, our career so far has been a failure, but I'll try to regress that in a few minutes. So let me now show you a movie that illustrates the formation of a dark matter halo. And here is the clock ticking. G stands for giga-year, so, which is a billion, so it's 70 million years after the Big Bang. Here's the scale. You're going to see the formation of a dark matter halo like the one in which we believe our Milky Way galaxy formed. Let me get the finger out of the way. And you see here, this was a quantum fluctuation, or many quantum fluctuations. What you see here is the distribution of dark matter interacting only through gravity. And you see how these gravitational interactions very soon turn these quantum fluctuations into this very intricate pattern. It's a filigrane of crisscrossing filaments. All these lumps of dark matter form along these filaments. At about this epoch, before the universe is even a billion years old, the first stars in the universe will begin to form as gas collects into these dark matter halos, and the universe will be lit up by the first generation of stars. Gradually, however, through the relentless force of gravity, these lumps fall together and building ever larger structures, and hence the name hierarchical cosmology, because structures form by accumulation of smaller substructures growing ever larger. You see what happens when some of these things go through, they get stripped, and this one liked it, so it's coming back for more, and there it goes, and every time it goes through, it loses a lot of the mass just through gravitational interactions. So here, by the time the universe is about 3 billion years old, most of this merging activity, we call these mergers, most of the merging activity has subsided, and now the conditions are right for clouds of rotating, spinning gas to cool, collapse, and then become unstable, cool into a disk, become unstable, fragment into stars, and produce a galaxy like the Milky Way. So that is the picture, and here things get a little bit boring after 6 billion years, so I won't keep you here for another 6 billion years. Instead, I'll move on to tell you that that movie, of course, was not made with that machine, and the simulations from which this movie is made was made at supercomputer 20 years after I first worked in Jülich, one of the large supercomputers in Europe, which is 800 teraflops in speed, where the tera is a trillion. The number to remember is that the machine where we moved that movie was a mere billion times faster than the original machines we had in the 1980s. However, undeterred by these little computing power we had at the time, we proceeded to simulate the formation of halos with all of 1,000 particles. Here are 6 cold dark matter halos that we simulated in the 1980s. And you can contrast those with the ones that Volker Springel and collaborators in the Virgo Consortium simulated 20 years later. Here are another 6. You can see certainly the graphics have got a lot better. And we can now study the formation of the halos with a lot more detail and in a much more comprehensive fashion. But actually, I thought it would be a good exercise to compare the largest halo we had in 1988 with 4,000 particles, shown here, with the largest halo we had in 2008 with 1 billion particles, shown here. Actually, if you look, they actually don't look that different, and they're elongated in the 2 cases, and actually they're centrally concentrated, and they have some substructure left over. Now, what's quite amazing actually is that this was really exhilarating because we were computing the properties of these 1,000 particle halos for the first time. We didn't even know what was interesting to compute, so we tried to compute everything we could think of. So for example, we computed something called rotation curves, which tell us how the dark matter is distributed in the halo. We worked out how these halos were spinning. and we worked out the shapes of these halos. We were surprised when they turned out to be round, but as you could see, highly elongated. We were good at counting, in spite of what George said, and she made at this point a low knob. That bug that Mark was talking about, it was me. And it was me because I couldn't read George's notes. At any rate, we counted the number of halos, it's now called the halo mass function, and encouraged by the exuberance of youth, we even went as far as trying to make an analogy between the dark world and the visible world. We used something that's now called halo abundance matching to try and guess where galaxies would form in these dark matter halos. Now, Simon never ceases to remind us these results have not changed in 30 years. The computer was small, the number of particles were small, but the physics was right, and it's really the physics that matters. And although, of course, we've done a lot better since and created a lot of more detail, the basic ideas were already there. And here's a real example of the exuberance of youth. We wrote a letter to Nature arguing that in such a universe, the cold dark matter universe produces objects with the abundance and characteristic properties inferred for galaxy halos. That was okay, but we got taken to task for the next sentence. Our results imply, but not that merging plays an important part in galaxy formation. This was the controversial part, suggests a possible evolution for the whole sequence. That's the sequence of morphological types of galaxies. How could we infer that from dark matter simulations? Well, we could, because we were young and optimistic, and that is encapsulated in this picture taken outside my house. There was an election then, you can see here Labour Party poster, in 1987. Now this is not any Kabbalistic sign, it says CDM, cold dark matter. So, where have we gone from there? Well, 10 years or 15 years after that work, with Julio Navarro, Simon and I, discovered a very interesting regularity. We found that these dark matter halos of all objects in the universe, from dwarf galaxies to galaxy clusters, all exhibited a very simple density profile. That's just the way in which the density is arranged inside the halo, could be described by a very simple formula. Now this was exciting because it provided a means to test the cold dark matter theory in a very rigorous way against astronomical observations. So let me just tell you two quick highlights of that work. You might wonder, well, how can you test dark matter? We don't see dark matter. Actually, we do see dark matter, and you see it, for example, in this phenomenon of gravitational lensing that's beautifully exposed here. What's going on here is there's a galaxy cluster which has lots of dark matter, and that galaxy cluster has distorted the images of background galaxies through this phenomenon of gravitational lensing that Einstein introduced. And by studying the distortions of these distant galaxies by the intervening dark matter, astronomers are able to figure out how the dark matter is distributed in the cluster. And here's some recent data that show this density as a function of radius. So these are the predictions of cold dark matter theory here in red, and these are data that you can see agree extremely well with the predictions. So this is a feather in the hat of cold dark matter. Galaxy clusters look good, but in the last couple of years, we began to cast a little bit of a shadow, no pun intended, in cold dark matter with the study of dwarf galaxies. It turns out that the Milky Way galaxies are surrounded by satellites that are very small, hence the name dwarf, and have very few stars, but these are ideal galaxies for the dark matter physicists because they're mostly made of dark matter. They have enough lights, enough stars for astronomers to find them and study their properties. And it appears that these satellite galaxies are doing something which is not what the doctor ordered. And here is a simulation of a galactic dark matter halo. We expect the satellites to form in these lumps that you see here. And recent data, possible only with the newest generation of large telescopes, seem to suggest that these halos, these subhalos, do not have cold dark matter subhalos the right properties to host the satellites. So there seems to be something not quite right with the theory, and so finally, after 30 years, we're now beginning to consider that perhaps the dark matter might not be what we thought it was for so long. It could be a different kind of particle. Now, you heard the citation. The citation mentioned cold dark matter. I'm now telling you maybe cold dark matter is not the answer. Do I need to give the prize back to Patricia? Warm dark matter works a lot better than cold dark matter. But I don't think I need to give the prize back, because in fact, on large scales, a warm dark matter universe, cold dark matter universe is essentially indistinguishable. So on large scales, everything we've done over the last 30 years still goes through, but of course, from the point of view of a particle physicist trying to find these particles, it makes a very big difference whether it is a cold particle or whether it's a warm particle, because they are completely different types of particles. So, let me then finish off just by saying that ultimately, finding out what the dark matter is an experimental physics problem, and luckily, however, there are experiments that might detect the dark matter either directly or something that's very exciting, that the Large Hadron Collider might actually make dark matter, if it is called dark matter, because it's supposed to create conditions in the universe in billions of a second after the Big Bang when these particles would have formed. If it is warm dark matter, there are also experiments on the way. So let me just then finish by showing you a picture of the view from my office in Durham, and I think there's been tremendous progress really in cosmology over the past 30 years. But the great thing is there's still a lot more to come.
How do I advance it? So, unlike my compatriots, I actually know enough about technology to know how to put this thing on. So I'm going to finish by talking about large-scale structure. So I started as a graduate student in astronomy in 1973. And I was impressed then. This was about the time that people were actually starting to take dark matter halos seriously. This is quite surprising, because the need for dark matter had been shown by a number of people, but in particular by Fritz Zwicky in 1933, pointing out that galaxy clusters needed a large amount of dark matter to explain their properties. People didn't know what to do about this, so they basically ignored it for a very long period of time. Fritz Zwicky was a very interesting character. He also made enormous contributions to galaxy clustering, gravitational lensing, theory of supernovae, many other aspects of astronomy, and he had a healthy attitude, let's say, towards dogma in astronomy. So Fritz was one of the, in fact, if you ever go back, there's a book called Morphological Astronomy. If you look at the introduction to it, you'll find interesting things said about the astronomers of the 1970s. So Fritz Zwicky, as I say, suggested that there should be a lot of dark matter in objects like galaxy clusters. And this was one of the things that I found most inspiring when I was starting, because here was something which really didn't fit anything. And the other inspiring person for me, I never met Fritz Zwicky, but I did meet Beatrice Tinsley. Beatrice put forward the idea that we should study galaxies as a population and understand their properties as a population, and this could be understood through astrophysics. And I still believe this is the way we should try and understand how galaxies form. So when I started, this was the dominant telescope in astronomy, the 200-inch telescope on Mount Palomar. I was lucky to go and visit it as a graduate student, and I actually got to sit in the prime focus cage, but I wasn't allowed anywhere near the telescope to actually use it. I actually used the Palomar 2-inch telescope, and fortunately Malik and I did some interesting work with it at the time. This though was the main instrument for my thesis. This was the main computer in Cambridge. It was an IBM 370. I never saw it because it was kept in a building in the center of town behind locked doors, and it was impossible to get in. What I saw were things that looked like this. I was going to ask if anybody under 30 actually recognized what these are, but somebody already gave away. These are machines for punching cards. When you punch the cards, you write each line of your program onto a punch card, then you put the cards in a box, and then they have to take it to a place like this where somebody would put it into a machine to read the cards. In our case, this was across a main street, about 500 meters away. And in Cambridge, it's not always sunny, so you would have to take this box of cards out in the rain across the street on your bicycle to put the cards into the card reader. If you dropped them, it was bad news because they fell out and then the order was randomized. And surprisingly, if you randomize the order of the instructions in a program, it doesn't work. We didn't have plotters. The way we made plots in those days was you took paper for printout was on what was called line print paper. It was a printer which printed out on paper this wide, and it printed out 126 characters across and then line after line. So these plots, which is from the published version of my first cosmological simulation, were made on line printer paper. If you look very carefully here, you can see these are actually just characters on a printer paper, but if you reduce it, it doesn't look too bad. And what we saw was that if you start with an expanding sphere of matter particles, expanding with the universe, we thought it was just going to fall back and collapse and make a smooth cluster, staying spherically symmetric, but it didn't do that. It became very lumpy, with many lumps. And the lumps fell together and made 2 lumps, and then eventually it all fell back together and made something nice and smooth. So this was a revelation when we saw it. I remember discussing it on the floor of the coffee area. And it was luck that happened, that this happened in 1977, and the Einstein Observatory flew in 1980 and actually made the first images of galaxy clusters in the X-rays. And look, there were irregular clusters, and double clusters, and clusters with a center. So you get encouraged. Maybe all these computer games actually have something to do with the real world. But then, as Marc told us, I went to Berkeley. And this was about the time that a Russian experimenter claimed to measure a mass for the electron neutrino. They claimed about 30 electron volts. And it so happens that a mass of 30 electron volts for the neutrino would mean that the total mass of all the neutrinos in the universe would supply all the dark matter. So this seemed amazing. So we thought maybe neutrinos are the dark matter. And I went to a conference at this time in Sicily somewhere, and I met Sergei Shandarin, who showed me, this picture, which is what he thought the structure looked like in a neutrino-dominated universe. And it had long filaments. We call this the cosmic chicken. There's the head, the feet, and the tail. So long filaments joining objects together. And this looked much more like Marc's survey than what we've been doing before, which is an example here. We've just got lots of blobs, as George showed us. So then Marc, Carlos, and I copied exactly what Clippan and Shandarin did and made our own blob plots. And we thought, well, these look much more like the real universe than these. But we hadn't really done the job very well, because the difference between the neutrino model and all these other models is actually, if you calculate things properly, as Dick Bond, the previous Gruber Prize winner, and George were doing, you can actually predict precisely what the initial conditions should look like, and then you can predict really what the universe should look like, how big everything should be, and when it should form. When we did that, the result looked like this. So this is Marc's survey, and these are our predictions when we put the real initial conditions expected for a neutrino-dominated universe into the computer. And they came out looking like here. Here are three different neutrino universes. In the neutrino universes, you get 1 or 2 huge clusters and huge low-density regions. Didn't look anything like the real universe. And this is because things were just too big. Now, this in some ways was a very successful paper. People looked at this and said, well, that doesn't work. We'll have to do something else. The problem with that is if they're convinced it doesn't work, they all give up working on it, and they all forget about the paper. So I think it's worth thinking about this, because the neutrinos are still the only particles that are known to exist, which could be the dark matter. And you ask, when outside astronomical measurements do we actually find out that this was not going to work? Well, it wasn't until 2006 that particle physics experiments finally showed that the most massive of all the neutrinos, the tail neutrino, couldn't be 30 electron volts. This was from neutrino oscillation experiments, which showed that the mass differences with their neutrinos are too small. So we ruled this out in 1983. It took until 2006 before this could be affirmed by the particle physics experiments. Nevertheless, after 1983, nobody worked on this model. So, as you've heard, we tried cold dark matter. We don't know if this particle exists, but maybe it looks a bit more like the universe. And here we are. These are 2 cold dark matter universes. They look a whole lot more like the real universe. But are they good enough? You look at the real universe, you can see here's a filament. This is the coma cluster. It's a filament. Here you can see a large low-density region. You look at our universes here, these assumed that the universe was full of cold dark matter. There's a flat universe, and all the matter was cold dark matter. And this is what we predicted it to look like. You can see these low density regions and these large scale structures, they're not really there. And as George, with his observational hat, at the same time, was doing work to measure structure in the universe, he came out with these measurements. So what you're seeing here, this is a measure of structure in the universe on a 10th of the degree, 1 degree, 10 degrees. This is just a measure of structure in the sky. And this is from a survey like Marc's, but much bigger. And these are the measurements, little dots. And the prediction for our nice, standard, flat universe filled with CDM was this dotted curve. It's great here, but it misses in the large scales. It just didn't have as much structure as there was there in the universe. So it turned out it's better, but it's still missing something. So there were three possibilities, really. It could be the universe wasn't flat. Theorists hated that because then it meant inflation had a problem. It could be there was a new kind of relativistic material that we didn't know about. Or it could be it was a cosmological constant. And George, in this paper in 1990, argued strongly that the correct, well, no, the most plausible answer was that it has a cosmological constant. So he shows this plot and says, we argue here that successes of CDM can be retained and the new observations accommodated in a spatially flat cosmology, which 80% of the critical density comes from the cosmological constant, which is the same as having non-zero energy density. Why did he pick this solution? It's because he really wanted the universe to be flat, because he believed in inflation. Another paper in Nature, Carlos and I came around to the same conclusion about 1993. This was for a different reason. When you look at a galaxy cluster, you can see from the X-rays that about 17% of all its mass is gas, it's baryons. We know in the real universe from nuclear synthesis it's only 4%, so that's, the dark matter is only 6 times as much as what you see. We know from nuclear synthesis that the baryons are only 4% of the density of today's universe. So you multiply by 4% by 7, you only get a quarter, you don't get 1. We showed from simulations we couldn't find any way around this, so we concluded the universe had to have low density, and therefore, in the text later on it says, one way to keep the inflation is to make the universe flat, is with a cosmological constant. And by 1995, even people in Princeton had come to the same conclusion. The combined observations point to models in which the matter density of the universe falls well below the critical energy density required to hold its expansion, but they also permit a substantial contribution to the energy from the vacuum itself, sufficient to recover the critical density. So you can see by the mid-1980s, the theorists, the theoretical cosmologists, all wanted a flat universe with a cosmological constant which would be exponentially expanding. Now, of course, there's a very famous quote, Virginia will know who it originally came from, that the cosmologists are often in error but never in doubt. But you know, sometimes they are correct. So theoretical prejudice can be right. So this, although this was the theoretical standard paradigm, in fact it did turn out the universe is accelerating. And this, of course, is what the Gruber Prize was given for a few years ago, and this year's Nobel Prize was given for discovering the universe is accelerating. And then the microwave background experiments about the year 2000 show that it is in fact flat, and Dick Bond got his Gruber Prize in part for this analysis. So, in this case, by a miracle, the theoretical prejudice of the mid-1990s turned out to be the correct answer. So, we'd said for how long? At least 10, maybe 15 years, that the universe is filled with matter. It's an Einstein-C universe, and all the observers have got the answer wrong because they don't understand that the galaxies are not distributed like the dark matter. But now it turns out that actually today the galaxies are distributed like the dark matter, and the density is not close to the critical density. So were we wrong? No, we were just ahead of our time. Actually, you could say we were behind our time. Because if you go to the early universe today, measurements show that this is in fact exactly the situation in the universe at a redshift of 2 or 3. But it's not true any longer. So this is just showing this. So this is Millennium simulation today, the dark matter and the galaxies. So you go back in time, this is redshift, this is today, redshift 1.4, redshift 6, redshift 9. So you go back in time, the dark matter is smoother and smoother. If you look at the predictions for the galaxies, you go back in time, there are fewer and fewer galaxies, but they're still just as inhomogeneous, just as clustered as they are at redshift 0. So if you go back to redshift 2, the density of the universe in dark matter is very close to the critical density, but the galaxies do not follow the dark matter, and if you were an observer back then, you would think the universe was open. So where are we today? This is the biggest simulation. It was the last point on George's plot of exponentially growing simulations. This is simulation was carried out by Raoul Angel and Volker Springer last year. This is now 3 times 10 to the 11 particles. So it's 30 times bigger than Millennium Run, 200 times bigger in volume, a bit lower resolution. This is where the math is predicted to be. So you zoom in on this. So this from here to here is a large fraction of the observable universe. If you zoom into this bit, you get this, and if you zoom into this bit, you get this, and if you zoom into this bit, you get this. You model where the galaxies should be, and get a single plot. So you can ask now, are we going to get a surprise again? So I don't know really what the answer is here, but here's one thing that surprised us. We looked at the structure in these simulations, and so people today are very focused on looking at structures on very large scales. So this, you don't really know exactly what this is. This is what's called baryon acoustic oscillations. These are variations in the amount of structure on very large scales. This corresponds to about 100 megaparsecs, 300 million light years. And then this is the predictions of the model for galaxies that are very common, very common, less common, very rare galaxies. And you can see these features, and these features are supposed to allow us to measure the accelerated expansion of the universe. There are lots of big surveys trying to measure this. They're also always supposed to be in the same place. But actually, if you look at this carefully, you can see they're actually moving. They're not in the same place for the different kinds of galaxies. So the galaxy formation may be causing us some problems here, because how can we measure this feature if it moves depending on which galaxies you choose to look at? So Volker Springer made this, and he put this sign here because he wasn't sure whether this is right yet, so maybe this will go away. But this is how we may yet get some surprises when we compare such large simulations with the real universe. So what we've been hearing is how we use computer simulations to see what our universe is like. And here, this is a movie due to Volker. We're flying through the universe inside the computer. Virtual universes have some advantages. Here we're flying at 10 to the 15 times the speed of light. You actually can cross the whole universe in 2 minutes. So that's an advantage if you want to see what it looks like. You can also see the dark matter, which is also an advantage. So this is, according to the simulations and Volker's talent for making movies, what today's universe would look like if it was made of dark matter, cold dark matter, or warm dark matter. Is this the correct answer? We still don't know. We won't know this is correct until we find some way to really tell what this elementary particle is, if it is in fact an elementary particle. So we have to find other ways to see this dark matter, not just inside our computer, but inside our experiments. So my hope is we will do that soon. Thank you. Take questions if anybody has any. But you'll have to tell who you want to ask the question of or who you want to answer. Virginia.
How are you going to improve things in the future?
Well, if you want the positive view, you should ask Carlos. I think the most obvious thing is we've just told you a lot about simulations of dark matter, and very little about simulations of things we can actually see. So clearly what we need to do is to understand better the things that we can see. And of course we're working on that, but it turns out to be much more complicated. Partly because you can see it, and partly because it is just more complicated. Anyone else want to add to that? Any other questions?
Thank you, and congratulations again. And this concludes our program. And there's a reception in the lobby beginning in just a moment. Yes, thank you.
coming to the section over at MPA. Those over here, up the stairs, and then those to MPA.
Someone who knows which way we're going should leave.
What's there?
Hey, David. Sarah's telling them all that we're going to get some stage shots right now.
That'd be good
So.
because
Yeah, I know you didn't really have much maneuver.
Well, and they also pinned the two at the same time.
Yeah. So if you want to just come, if you can come around here, this camera is.
Let me just get my other camera real quick. Because sitting back here.
But yeah, then we'll go to there. So. Oh, there you got it.